In this video, I'll show you how to make a pinhole projection viewer to safely view the sun during a solar eclipse. Before we begin, I'll show you what the eclipse looked like from inside the viewer. Okay, here's the eclipse from inside the viewer in a time lapse. You can see the sun moving across the inside of the viewer, and this required me to reposition the viewer several times during the eclipse itself. But you can see here we went from pretty much full sun to about 89% eclipsed, and then back again to full sun. I have another time lapse from an iPhone with a solar filter showing the eclipse, and I'll put a link in the description below. So I'll show you here how I made the pinhole projection viewer to watch the eclipse. Really just needed to buy a 4-foot by 4-inch mailing tube, some foil, used an X-Acto knife and a pin, and let's get this started. So basically the hole that you cut in the side is so that you can view the image of the sun here on the bottom plate. And that image comes through at the end from a pinhole that you puncture in foil wrapped over the side of the tube that you'll point towards the sun. So when you get your mailing tube, at one end, just pop off the plastic cap, then take a very sharp X-Acto blade or a box cutting knife and mark a hole roughly 2 inches by 2 inches, or in this case 2 by 3, about an inch or less from the other end, and then cut out that square of the tube. And this will make your viewing port to see on the bottom of the tube. If your tube comes with white plastic end caps like mine did, which are quite thin, you'll see some light even from in the room may glow through. So you can stuff a round piece of black construction paper on the back side of the end cap to minimize the light that can leak back in to the tube. Now on the inside, you can just put a piece of white paper to provide a reflective surface to see the image of the sun. But in my case, I put a piece of very fine graph paper because we're going to do a measurement at the end of the video for the sun's diameter. Now you can use pretty much any graph paper, but the smaller the markings, the better. This one I have is very thin paper. It's a very old paper that has 20 by 20 per inch. And this actually worked out really well. Basically what you do is take a sheet of your graph paper and you lay it over your end cap that you're going to use for your viewing screen, and then take your tube and mash it down over the graph paper. It will stretch and pull the paper and make a nice flat surface inside for viewing. Okay, back on the other side, we're going to take a sheet of aluminum foil and just lay that over the top of the open end of the other tube and pull it taut around the end, just like that. Once that's on, and it doesn't have to be perfect, you don't have to put a rubber band on it, but I grabbed a large rubber band and just used it like that around the rim to hold that foil in place. And then take a pin, very circular and as thin as possible, and just puncture a hole in the center of the foil. You can spin the pin a little bit like that, make a circular hole, and pull it straight out. Don't bend it and try to make the hole wider. Actually, the smaller the hole, the better. There it is. And then you'll aim this end towards the sun, and don't look at the sun. And then the sun's image will come through the tube and project on the inside here. And now what we'll try to do is use the images that we took during the eclipse, see if we can calculate the sun's actual diameter from the measurements that we made. So here's an image of the sun on the graph paper before the eclipse, and you can see there's about 9.5 squares. So I just drew out on the graph paper about the size of the sun image that we had inside the Pinhole viewer. And I had measured, as you just saw, about 9.5 of the graph paper squares across the diameter. And we know that this paper is 20 squares to the inch, and we have 9.5 across. I also know that the length of the projection tube here is 48.5 inches, and I'm measuring just to the inside where the surface of the screen is, because that cap comes in a little bit. Okay, so we have 48.5 inches for the length of our tube. So back to our image of the sun, we had 9.5 squares. We know 20 squares is an inch, so 9.5 over 20, and we solve for x, we get 0.475 inches. Now if I measure it with a ruler, even though I realize this is not as precise, I count 15 30-seconds. So 15 divided by 32 gives me 0.4687, which is close. So we'll run both numbers. So I've written down here the 0.4687 using the ruler measurement as an alternate. So you can see they're pretty close. Okay, so I took those two dimensions of the diameter of our image, converted from inches to feet. Again, I'm ignoring significant digits here. This is just an approximation, but we'll run it with both of these numbers. So if you imagine the sun here on the left, where this big H is the diameter, and all that light is shining through the pinhole. This is our cardboard tube. From the pinhole, travels down the length of the tube and makes this image on the screen, which has a diameter that we'll call little h. So the length of the tube is that distance, lowercase d, and the distance from the pinhole to the sun itself is this, and this is the formula that we use. So we want to figure out the big H, the actual height or the diameter of the sun. We can look up online the distance from the sun to the earth, or in this case to our pinhole projection, and as of today online we get about 93 million miles. Convert that to feet is this number here, again ignoring significant digits. So we know the two values we have for the image, h 0.03958 or 0.03905 in feet, and we know that the length of our tube is 4.0416 feet. So we solve for h. The diameter of the sun is the distance from the pinhole to the sun multiplied by the diameter of our image divided by the length of our tube. Okay, so the first number, I used the calculation of the diameter of the image based on the squares on the graph paper, the 0.03958 in feet. And so we plug in for the equation to solve for the diameter of the sun, the distance from the Earth to the sun in feet times the diameter of our image in feet divided by the length of our tube in feet, and then we get this number here, and I convert that to miles. 1 mile is 5,280 feet. So when we solve that, we get the diameter of the sun of 911,761 miles and change. Okay. We can do this again using the other number, and we calculate a diameter of the sun of 899,566 miles and change. So we're somewhere between about 912,000 miles. So I compared this to some values I found online for the actual diameter of the sun today on one of NASA's websites, and I'll put links in the description to these. NASA's reporting 865,000 miles, and space.com is reporting 932,057 miles. Both of our numbers fall within this range, which is pretty amazing to me. I didn't expect it to be that close. So when I run the comparisons there, our low number, that's about 4% off of the low value, the NASA number. And our larger number is about 2% off of the higher value of 932,057 miles from space.com. And last, just that low number again, that's about 3.5% off of the space.com number. So we're really within, say, 3 to 4% of the actual value. And last but not least, here's some data from our personal weather station taken during the eclipse. As you can see here, we started out with a temperature around 73 degrees, and at the peak of the eclipse, we got down to 67 before coming back up. We also had watts per meter squared over 1,000 right before the eclipse, and then down to the low 60s during the peak of the eclipse. Thanks for hanging in there on this long video, and thanks very much for watching.